Hello students, in today's lecture we are going to learn about electric charges and fields, and this is theory part 2. In the previous lecture we studied Coulomb's law for two charges. In this lecture we will extend our understanding to systems with multiple charges. We will learn how to calculate electric field due to multiple charges, and also we will learn concept of electric flux. Disclaimer: the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the same. Forces between multiple charges. So, as shown in figure, there is a multiple charges Q1, Q2, Q3. System of three charges, or we can say multiple charges in figure B. Q1, Q2, Q3, Q4 and Q5. So, the mutual electric force between two charges follows Coulomb's law. But when dealing with multiple charges, in that case, we need to consider how these forces interact. It means if we have more than two charges, we need to consider how these charges interact. For a system of n stationary charges, and that n stationary charges are Q1, Q2, Q3 and Qn in vacuum, the force on Q1 due to other charges is determined by the principle of superposition. So, using the principle of superposition, we can determine the force on a single charge due to other charges. This principle states that the force on any charge due to multiple charges is the vector sum of individual forces. So, this is the statement of the principle of superposition, with each force unaffected by other charges presence. Let's take an example. In a three charges system, look at figure A, Q1, this is three charge system Q1, Q2 and Q3. O is the origin. The force on Q1, the force on charge Q1 due to Q2 and Q3 is found by vector addition of individual forces. So F1 2, it means force on charge first, F1 2, force on charge first due to charge second. So Q1, force on Q1 due to Q2 is 1 F1 2 is equal to 1 upon 4 pi epsilon naught Q1 Q2 divided by R square 1 2. Here 1 2 means force on charge first due to second, and R cap is the direction of the field, direction of the force. Similarly, if we talk about the force on charge first due to charge 3, on Q1 due to Q3 is F13, 1 upon 4 pi epsilon naught Q1 Q3 divided by R square 13 R cap 13. So the r cap denote the direction of the force. Look at here. Here we consider that we have to find initially force on charge first due to second. Now q1 q2, if we consider q1 q2 are both positive charges, means like charges, in that case the direction is away in right side. And force on charge q1 due to charge q3 is f13, and the direction is away, because if we consider here q1 and q3 are positive, then direction is outward. This one, this is one, this is the direction of force 13, and this is direction of force 12. Now what will be the net force on the charge q1? So here the net force on charge q1 is f1. F1 is the net force. This is the vector sum of individual forces on the charge, or we can say on a single charge. So a system of three charges, the total force F1 on charge q1 is vector sum of individual forces. F1 is equal to force on charge first due to second plus force on charge first due to third. Now what is F12 and what is F13? So F12 is 1 upon 4 pi epsilon naught q1 q2 divided by r square 12 and r cap 12 plus F13 1 upon 4 pi epsilon naught q1 q3 divided by r1 r square 13 r cap 13. So this is the vector sum of individual forces and net force on the charge q1. I hope this is clear. Now if we consider n charges, so in that case for n charges the total force on q1 is, this is the net force on charge q1 due to n charges, that is F12, it means force on charge first due to second plus force on charge first due to third plus force on charge first due to nth charge. Clear? Now take 1 upon 4 pi epsilon naught common, because this is common in every force. So 1 upon 4 pi epsilon naught common. So it will be q1 q2 divided by r square 12 r cap 12. Similarly q1 q3 divided by r square 13 r cap 13. R cap is the direction. Here is the unit vector. Now force on charge q1 due to nth charge, that is q1 qn divided by r square 1n r cap 1n. So this is the for n charges, force on a single charge due to n charges. I hope this is clear. Now in simple terms we can write this F1 is equal to q1, because q1 is common in every force, F12, F13 and F1n. So q1 q1 and q1. So take q1 common, and 1 upon 4 pi epsilon naught is also take common. So it will be q1 divided by 4 pi epsilon naught summation I is equal to 2 to n. So qi divided by r square 1i r cap 1i. So this is the representation of force on single charge due to multiple charges. Clear? If we resolve this summation, you will be get again this one. Clear? Put the value of I is equal to 2, you will be get in that case this one. Then I is equal to 3, you will be get this one, and so on. So this is the force on a single charge due to multiple charges. Example, consider three charges. We have a three charges Q1, Q2 and Q3, each equal to Q at the vertices of an equilateral triangle of side L. What is the force on a charge Q, capital Q, with the same sign as Q, placed at the centroid of the triangle as shown in figure? So look at here. So O is the centroid of the triangle. Now here Q1 is equal to Q, Q2 is equal to Q, and Q3 is equal to Q. And here we have to find out the force on charge Q, which is placed at centroid of the triangle. Clear? Solution. In the given equilateral triangle ABC, A, B, C, of sides of length L, if we draw a perpendicular AD, this one, to the side BC, so in that case AD is equal to AC cos 30. AD is equal to AC cos 30. Look at here. AD is equal to AC cos 30. And we know cos 30, AC is what? AC is L and cos 30 is root 3 by 2. So AD is equal to root 3 by L. Root 3 by 2 multiply with L. And the distance AO of the centroid O, the distance of AO from A is 2/3, or we can say 2 by 3 of AD. So it will be what? It will be 1 divided by root 3 multiply with L. So this is the given data. Now by the symmetry AO is equal to BO and BO is equal to CO due to symmetry. It means all sides, it means AO, BO and CO are equal. Thus, force F1 on charge Q, which is placed at the centroid due to charge Q at A. Charge Q placed at point A, similarly other charges placed at different positions. So it will be 3 divided by 4 pi epsilon naught Q divided by L square along AO. AO. So here the direction of force Q1 is also positive and Q2 is capital Q, which is placed at centroid, is also positive. So direction of force along AO, repel. Force F2, look at here, F2 on charge Q due to charge small q, which is placed at B, that is 3 divided by 4 pi epsilon naught Q divided by L square, and the direction is along BO, B2O. Now the remaining force is F3. So force F3 on Q due to charge small q at C, small q placed at point C, look at here, this one. So F3 is equal to 3 divided by 4 pi epsilon naught Q divided by L square along CO. Look at here, this one. So this is the all forces F1, F2 and F3. Now what will be the resultant force according to the principle of superposition? The resultant of forces F2, F3 is 3 divided by 4 pi epsilon naught QQ divided by L square along OA. OA. So the net resultant force acted along OA by the parallelogram law. So this comes from the using by the parallelogram law. Therefore, the total force on Q that is placed at a centroid of the triangle, it will be 3 divided by 4 pi epsilon naught QQ divided by L square, and R cap minus R cap is equal to 0, where R cap is the unit vector along OA. It is clear also by symmetry that the three forces will sum to 0. Suppose suppose that the resultant force was non-zero. If the resultant was non-zero, but in some direction, consider what would happen in that case if the system was rotated through 60° about O. So consider the charges Q, Q and minus Q placed at vertices of an equilateral triangle as shown in figure. What is the force on each charge? Look at here. This is equilateral triangle, and here we have to find out the force on each charge. The force is acting on charge Q at A, point at A, due to charges Q at B and minus Q at C are F12 along BA and F13 along AC. I hope this is clear respectively as shown in the figure. I repeat it. So F12 is the force on charge Q1 due to charge Q2. F13 is the force on charge Q1 due to charge Q3. Clear? Now F1 is the resultant force on charge Q1. Similarly, F31 is the force on charge Q3 due to first, and F32 is the force on charge third due to second, and the resultant force on the charge Q3 is F3. Similarly, force on charge Q2 due to charge Q3 is F23, and force on charge Q2 due to charge Q1 is F21. And what will be the resultant force? That is F2, that is acted on charge Q2. So this is the force due to three charges system. So F1 is equal to F R1 cap, this one, where R cap is the unit vector along BC, B to C. The force of attraction or repulsion for each pair of charges has the same magnitude for each pair F12, F31 and this one F1, F2, F2 and F3. The magnitude is same. So that is F is equal to Q square divided by 4 pi epsilon naught L square. So the total force F2 on charge Q at B is thus F2 is equal to F R2 cap, where we know R2 cap is the unit vector along AC. R2 cap shows the direction of the force. That's it. Clear? Now, similarly, the total force on charge minus q, that is q3 at C is F3 is equal to root 3 F n cap, where n cap is the unit vector along the direction bisecting the angle BCA. Angle BCA. It is interesting to see that the sum of the forces on the three charges is 0. So F1 plus F2 plus F3 equal to 0. The net force is 0. So there is a two images A and B. Electric field, A shows the electric field due to a charge and Q, that is positive charge, and in figure B due to a charge minus Q. For look at here, for the field, for the positive charge here outward, radially outward, and for the negative radially inward. This point is important, so remember this. The concept of electric field was introduced to explain how forces acts between charges across empty space. So basically, electric field is a space in which charges feel electrical effect. When a point charge Q is placed at origin O and another charge small q is placed at point P where OP is equal to R. So Q exerts a force on Q following Coulomb's law. We already learned the Coulomb's law in previous lectures. So electric field produced by charge Q at point R is given by this one. E of R is equal to 1 upon 4 pi epsilon naught Q divided by R square R cap. So it will be 1 upon 4 pi epsilon naught Q divided by R square R cap, where R cap is a unit vector. If we represent it in simple form, it will be R vector divided by magnitude of R is the unit vector from origin to point R. The field describes how a distributed quantity varies with position. The force F exerted by charge Q on charge Q is this one. This is the force exerted by charge capital Q on charge small q and the separated distance by R. So the force will be F is equal to 1 upon 4 pi epsilon naught QQ divided by R square R cap. The relationship between force F and the electric field E is F of R is equal to Q into E of R. So this relation is very important. So remember this point. This defines the SI unit of electric field as Newton per Coulomb. So this is the SI unit of the force here, electric field, Newton per Coulomb. Newton per Coulomb is the SI unit of electric field. Let's calculate. So here E of R is equal to what? E of R is equal to F divided by Q, and the unit of force is Newton and unit of charge is Coulomb. So it will become Newton per Coulomb. Some important characteristics of electric field. First is electric field at a point is defined as the force experienced by a unit positive charge placed at origin, or we can say placed at a point Q or we can say placed at a point O. So any point where Q is the source charge and small q is the test charge. Capital Q placed at a position which is source charge and small q is test charge. To avoiding disturbing, capital Q and small q should be negligibly small. So in that case, the electric field is equal to limit q extends to 0 F by Q. So it is very important. F is equal to QE. Second characteristic is the electric field E is independent of test charge. E is independent of test charge Q since F is proportional to Q. E depends on the space coordinate, that is R, and exists at every point in three-dimensional space. Clear? Positive charges, electric field points radially outward. This point is important. If the charge is positive, electric field points radially outward. If the charge is negative, it points radially inward towards the origin, outside from the origin. Clear? So this is the important characteristics about the positive charge and negative charge. If we talk about the electric field, look at here, A and B. A is the for the positive charge, so electric field points radially outward in all directions. And if we talk about the negative charge, so electric field radially inward. So this concept is very important. Clear? The magnitude of E depends only on distance r from charge q, showing spherical symmetry. Equal magnitude at equal distance from q. So look at here the figure. Electric field at a point due to a system of charges is the vector sum of electric fields at the point due to individual charges. So this is the electric field at a point. Suppose the point is P. Here electric field E1, E2, E3, E4 due to other charges. And the distance of the charges from the point P is this one, R1P. And this is the distance of charge first from point P. Similarly, R2, distance of the charge Q2 from the point P, and similarly so on. The electric field at a point in space due to system of charges, and the charges is Q1, Q2 and Qn with position vectors, means from the origin. Position vector means the distance measured from the origin. So the position vectors are R1, R2 and Rn for n charges. Relative to origin, O is defined as the force experienced by a unit test charge placed at that point without disturbing the original charge positions. So now, using the Coulomb's law and the superposition principle, the field can be determined at point P with position vector R. Clear? So we already learned the Coulomb's law and superposition principle. So look at here, E1, E2, E3 and E3 are the electric fields. So electric field at a point due to system of charges is the vector sum of electric fields at the point due to individual charges. For charge Q1, listen carefully. For charge Q1 at a distance R1, the electric field E1 at R is given by E1 is equal to 1 upon 4 pi epsilon naught Q1 divided by R1p square R cap 1p. Here the point is for the understanding is Q1 is the charge, we know, E, and 1 upon 4 pi epsilon naught is the constant term if we talk about in vacuum. R1p is the position vector from the point P if we talk about the charge Q1. So it will be R square 1p according to formula, and R cap 1p is the direction of the electric field. R1p, R cap 1p is the unit vector from Q1 to point P. R1p is their separation distance. So this is all about for the charge Q1. Now similarly for the other charges. For charge Q2 at R2, E2 is 1 upon 4 pi epsilon naught Q2 divided by R square 2p R cap 2p, where R cap 2p is the unit vector from Q2 P, and R2p is their distance from the point P where we have to find out the electric field due to charge Q2. I hope this is clear. This pattern continues for fields E3, E4 and En for nth charges, or we can say due to multiple charges. If we have n charges, then we have to find out the nth electric field due to n charge. So here electric En due to charge Qn, and similarly E4 for charge Q4 and E3 for charge Q3 and so on. I hope this is clear. For multiple charges, there is a multiple of electric field. So look at here. We already know this. So by superposition principle, the total electric field E at R is the vector sum. Clear? Vector sum of E. So when we find out the vector sum of the E at R, that is the total electric field. So E of R is the total electric field due to multiple charges. So E1 of R, E2 of R plus En of R. So it will be 1 upon 4 pi epsilon naught Q1 divided by R1p square R cap 1p. This is for E1 of R. Now E2 of R is this one. 1 upon 4 pi epsilon naught Q2 divided by R2p square R cap 2p, plus for the En of R, it will be 1 upon 4 pi epsilon naught Qn divided by R square np R cap np. So this is the electric field, or we can say net electric field at point P due to multiple charges. Clear? If we find out the electric field due to two charges, that is the Q1 and Q2 at point P, so only we take only two terms. If we find out the n charges, in that case we consider all the formulas and all the terms. So E of R in the form of summation, the net electric field at point P due to multiple charges of system, it will be 1 upon 4 pi epsilon naught summation I is equal to 1 to n. So Qi divided by R square 1p R cap 1p. If we put I is equal to 1 and I is equal to 2, 3 and 4, you will be get again this term. So this is just mathematical term to represent simply. Is the vector varies spatially and depends on source charge position. Clear? Physical significance of electric field. First is the concept of electric field, while convenient but not necessary for electrostatics, provides an elegant way to characterize the electrical environment of charge systems. It represents the force a unit positive test charge would experience at any point, and it is independent of the test charge itself. It is important point. E is independent of the test charge itself. Second physical significance is the true significance of electric field emerges in time dependent electromagnetic phenomena. For accelerated charges, effects cannot propagate instantly due to speed limit c, that is speed of light, and the field concept naturally explains this time delay. That is, accelerated charges produce electromagnetic waves that propagate at speed c to reach other charges and exert forces. About this phenomena, we will learn very briefly in upcoming lectures. Fields are considered physical entities with independent dynamics, not just mathematical constructs. They can transport energy, that is, time dependent electromagnetic fields can propagate and carry energy even after the source is switched off. This concept, introduced by Faraday, is now fundamental to physics. So, this is the some physical significance of the electric field. Example: an electron falls through a distance of 1.5 centimeter in a uniform electric field of magnitude 2.0 into 10 raised to the power 4 Newton per Coulomb. Figure A. Look at here. The direction of the field is reversed, keeping its magnitude unchanged, and proton falls through the same distance. Look at figure B. Compute the time of fall in each case. Contrast the situation with that free fall under gravity. Free fall under gravity means, suppose we have a ball and we dropped from this point, and balls fall vertically downward under the under the action of gravity. So there is only a force, that is gravity. So this is the free fall condition if we talk about a ball. So there is a electron. Let's see. So solution in figure A, look at here. The field is upward. Field is having upward direction. This one, positive to negative, upward direction. So the negatively charged electron experience a downward force. Negatively charged electron experience a force that is vertically downward of magnitude EE. Is where is the magnitude of electric field, and the acceleration of electron is A is equal to EE divided by ME. This formula is very important, where M is the mass of the electron. Starting from rest, the time required by electron to fall through A, it will be H is given by TE is equal to under root 2H divided by AE. So substitute the value AE, you will be get under root 2HME divided by EE. This one. So E is equal to 1.6 into 10 raised to the power minus 19 Coulomb. M is 9.11 into 10 raised to the power minus 31 kg, mass of electron. The value of E is already given in this question, that is 2.0 into 10 raised to the power 4 Newton per Coulomb, and H is 1.5 into 10 raised to the minus 2 meter. So here we have to find out the time of fall in each case. So for the electron, the time is 2.9 into 10 raised to the minus 9 second. If we substitute all given terms in this formula, we will get the value of t is this one. Clear? So in figure B, the field is downward. Look at here. In figure B, the direction of field is downward, opposite of figure A. This one. And positively charged proton experiences a downward force of magnitude EE. The acceleration of proton is EE divided by MP. MP is the mass of proton. Where MP is the mass of proton, so MP is equal to 1.67 into 10 raised to the power minus 27 kg. The time of fall for proton is Tp is equal to under root 2h divided by AP, under root 2h MP divided by EE. Just substitute the value of AP and you will be get this term. And put all given terms like MP mass of proton and H and value of E, capital E, and you will be get 1.3 into 10 raised to the power minus 7 second. Clear? So here the important formula is this one, 2h MP divided by EE and taking square root. Thus, the heavier particle, proton is heavier, takes a greater time to fall through the same distance. This is in basic contrast to situation to free fall under gravity, where the time of fall is independent of the mass of the body. This is important point. Time is independent of mass of the body. Note that in this example, we have ignored the acceleration due to gravity in calculating the time of fall. So to see it this justified, let us calculate acceleration of the proton in the given electric field. So the formula of acceleration is EE upon MP. So the value of E is 1.6 into 10 raised to the power minus 19 coulomb. Electric field is 2.0 into 10 raised to the power 4 Newton per coulomb, and mass of proton is this one. So calculate this, you will be get AP is equal to this one, 1.9 into 10 raised to the power 12 meter per second square, which is enormous compared to the value of G, that is 9.8 meter per second square, the acceleration due to gravity. The acceleration of the electron is even greater. Thus, the effect of acceleration due to gravity can be ignored in this example. Another example, 2-point charges Q1 and Q2 of magnitude is 10 raised to the power minus 8 coulomb and minus 10 raised to the power minus 8 coulomb respectively. So, this is the value of the charges placed 0.1 meter apart. The distance between the charges is 0.1 meter. Calculate electric fields at point A, B and C shown in the figure. Look at here. Point A is this one, point B and point C. This is point C and point B. So here we have to find out the electric fields. So electric field vector E1 A at A due to positive charge Q1 points towards the right and has magnitude this one. E1A is equal to 3.6 into 10 raised to the power 4 Newton per coulomb. So E1A, look at here. Here Q1, Q2 and Q1, Q2 are the charges. The value is given. in this question, and we have to find out the electric field. So E1 A is this one. The electric field E2A at A is at point A here. Due to negative charge Q2 points towards the right and has same magnitude. Hence the magnitude of the total electric field EA at A is this one. E1A plus E2A is equal to 7.2 into 10 raised to the 4 Newton per coulomb. We already learned the concept to find the electric field due to multiple charges. So there is only two charges. So in that case, the electric field EA is equal to this one. EA is directed towards right. Direction is right side. So the electric field E1B at B here, suppose at point here, is positive due to positive charge Q1. Positive charge Q1 points towards the left and has magnitude E1B is equal to 3.6 into 10 raised to the power 4 Newton per coulomb. So here Q1 and Q2 depends on their signs, positive or negative. So value of the magnitude is same, but direction depends on the signs of the charges. So electric field vector E2B at B due to negative charge Q2 points towards right and has magnitude this one. E2B is equal to 4 into 10 raised to the power 3 Newton per coulomb. So the magnitude of the total electric field at B is EB is equal to EB E1B minus E2B is equal to 3.2 into 10 raised to the power 4 Newton per coulomb. Because here E1B and E2B, look at here, E A have in right direction and this is EB in left direction due to charge Q1. So EB is directed towards left. So the magnitude of each electric field vector at C here is due to charge Q1 and Q2 is E1C is equal to E2C. The magnitude will be same, that is 9 into 10 raised to the power 3 Newton per coulomb. The directions in which these two vectors point are inclined in figure. The resultant of these two vectors is EC is equal to E1C cos pi by 3 plus E2C cos pi by 3 is equal to 9 into 10 raised to the power 3 Newton per coulomb. So EC is the net electric field. EC points towards right. I hope this is clear. We already learned this concept. Electric field lines. Electric field E being a vector quantity, it has both magnitude and direction, can be represented pictorially for a point charge at the origin. The vectors point in the field's direction with lengths proportional to field strength, decreasing inversely with square of the distance from charge. It means the we know is the vector quantity and it is inversely proportional to length or inversely proportional to distance, square of the distance. So here charge is positive. So electric field lines, listen carefully, charge is positive. So electric field lines radially outward, radially outward, and If the charge is negative, in that case, what happens? In that case, what happens? Figure a point charge, this one plus q, field gets weaker and density of field lines is less, resulting well separated lines. So, if the charge is negative, field lines radially inward. Field lines are obtained by connecting arrow pointing in one direction, pointing in one direction like this. The magnitude of the field is represented by density of the field lines. High density near the charge where the field is stronger. So, this is this question for you. So, suppose we have 2 points, A point and second one is B point. So, where the density is high, at point A and at point B near the charge, that is A. So, at point A the density is high and its electric field is much stronger. Clear? So, high density near the charge where the field is stronger and lower density further away where it's weaker. We know E is inversely proportional to R square. So, from this relation it is also clear, if R is greater than it means E is small. While infinite lines can be drawn, the relative density matters more than the absolute number. Look at here. Dependence of electric field strength on the distance and its relation to the number of field lines. And this is origin. In 3 dimensions, the density of field lines is considered per unit cross sectional area perpendicular to that lines. So look at here. We talk about 3 dimensional. So there is a reason P1. First is P1, this one, and second is P2. And if another reason, suppose another reason P3, so in that case, reason P1 is strong field reason as compared to P2 and as compared to P3. P2 is strong field reason as compared to P3. So, if we talk about P1 and P2, in that case, P1 is strong field because it is near the point. Due to inverse square relationship of electric field and with distance and proportional increase of enclosing area with square distance, the number of field lines crossing any enclosing area remains constant. For point P1 and P2 at distance R1 or R2, the areas subtending solid angle delta omega are R1 square delta omega and R2 square is delta omega. R2 square delta omega. Solid angle, this one for the P2 and for the P1. With n lines cutting these areas, the field strength follows 1 upon R square dependence. So, if R is vary, field is also vary. Faraday introduces these lines of force for visualizing electric fields. A field line is a curve whose tangent at any point indicates the field direction at that point, marked with arrows to show direction. Look at here, A, B, C or D. So, for the positive charge, field lines outward, and for negative charge, field lines inward. Field lines due to some simple charge configuration. So, there is a positive charge and there is a positive negative charge. Field lines provides a visual representation of electric fields in 3-dimension space, though typically shown in a plane. For a single positive charge field, single positive charge q is greater than 0, field lines extend radially outward in all direction, radially outward in all direction. While for a negative charge, q is less than 0, they point radially inward. This concept is very important. They inward towards the origin. In a system of two charges, suppose both charges are positive, that is q and q, the field lines illustrate mutual repulsion. Look at here. If the charges are positive, small q and small q, so field lines, there is a mutual repulsion. Whereas for a dipole configuration, so here question arises, what is dipole? A dipole is a system which consists two equal and opposite charges like capital small q and minus small q. So here two charges plus q and minus q. So this demonstrate mutual attraction between opposite charges. The field lines follow key properties. So some key properties regarding field lines. First is they originate from positive charges and terminate at negative charges. Look at here. Originate from positive charge and terminate to negative charge. I hope this is clear. Originate from positive charge and terminate to negative charge. Originate from positive charge and terminate to negative charge. Potentially extended to infinity for isolated charges. Second, in regions free of charges, the field lines form continuous curve without breaks. Field lines cannot intersect, and this is important point. Electric field lines cannot intersect. Why? As this would imply multiple field directions at a single point. That is not possible. Fourth is electrostatic field lines never form closed loops, reflecting the conservative nature of the electric fields. Look at here. Dependence of flux of the inclination theta between E electric field and n cap is the direction which is perpendicular on the surface. For electric field lines, number of field lines crossing unit area normal to field measures field strength. Look at here. The electric field lines crossing the area delta S, and here electric field lines crossing area delta S. So area element delta S tilted as small angle delta theta to E. So number of field lines is directly proportional to E delta S cos theta. This is important. Number of field lines depends on this term. When theta is 90 degree, no field lines cross the surface because cos 90 0. It means overall value is 0. So there is a no field lines. So delta S is equal to delta S n cap. Delta S, this one is the magnitude and n cap is the direction which is perpendicular to area element. So figure convention for defining normal n cap and delta S. Area elements, that is delta S, are treated as vectors. Direction is along normal to plane. So n cap shows the direction. For closed surfaces, direction is along outward normal. If the surface is closed, in that case, the direction is along outward normal. Area element delta S is equal to delta S n cap. Delta S is the magnitude, n cap is the outward direction which is perpendicular. Electric flux definition. So the mathematical form of electric flux E dot ds, where resolving the dot product you will be get E delta S cos theta. This can be interpreted as E delta S cos theta E times area projection normal to E. E is perpendicular to delta S component along normal times area magnitude. And unit is Newton per coulomb per meter square. Electric flux. So convention for defining normal n cap and delta S. Total flux. This is important. Total flux through surface S. Suppose we have a surface S. In that case, what will be the total electric flux? So phi equal to summation E dot delta S. So this is the total flux. The approximation sign is put because electric field E is taken to be constant over the small area element. This is mathematically exact only when you take the limit delta S approaches 0 and the sum of equation is written as a integral form. So in upcoming lectures, we will learn electric flux by using Gauss theorem. Thank you for your attention.